So here we're going to talk about volumes by cross-section. So let's think back before we jump into volume three-dimensional, we'll think two-dimensional. So area in the plane. So if I'm talking about area in the plane, I've got this curve f of x, my x and y axis here, and I want to find the area under that curve from A to B. Okay, so that's this area here. Then to do that, I do the definite integral starting at A, going to B. I'm adding arbitrary rectangles. So that's an arbitrary rectangle. Looks like this. I've got my dx here. And the height of the rectangle is top f of x minus bottom y equal to 0. So top minus bottom, that's f of x minus 0, which is just f of x. And then the width of that arbitrary rectangle is just your delta x. Okay, so this is your height. And then this is your width. Okay, and so height times width gets you the area of a rectangle, right? So here's what we're gonna do, okay? We're gonna take this weird looking object, okay? This amoeba looking thing here. Look, this is like trying to be artistic, doing the best I can. Please don't make fun of me, right? And so what I'm going to do with this shape is I'm going to try to figure out the volume of it, okay? And to do that, I'm going to use calculus. So I'm going to start it at this A and end it at this B here. And I'm going to make a cross section in the middle of it. And so this cross section, this delta x width, I'm going to cut out this piece here. And it turns out that these cross sections are tiny little cylinders. Okay. All right, so you can kind of see if I take that cross section out, it looks like this. All right. Okay. So a little cylinder with delta x width. All right. And the trick here is to cut the shape into small slices that are perpendicular to the axis that you're integrating with respect to. So you notice that this slice here is perpendicular, that's a 90-degree angle, with the axis, we're using this x-axis here, that we're integrating with respect to. So if I let a of x be defined as the area for a shape at a given x value, some arbitrary x value, okay? Then you think about it like this one little sheet right here, this circle here, that area, a of x here, all right? That would be like the area of a circle, right? So then the volume of that object would be equal to the integral starting from the first slice and then adding all the little cylinder slices to the last slice, so that sum from A to B, that's what that symbol means, if you recall. Okay. This is the area of the shape at the given x times delta x. And that tells you the volume. So this is our formula right here. So the volume is the area, A of x, for the shape at some given arbitrary x value. Okay, at some x, we have a width delta x, right? Okay, and so I multiply that area by the width to get that three-dimensional volume. Okay, so let's take an example here. So I'm going to do find the volume of the solid whose base is between x equals 4, y equals x over 4, y equals negative x over 4, and has cross sections that are perpendicular to the x-axis in the shape of a square. Okay? So what does this look like? So what I'm going to do first is I'm going to draw XY axis here, all right? And I'm going to draw the line x equal to 4. So I'm going to go out 1, 2, 3, 4. This is what you always do if you don't have graph paper, right? You just draw it. And so x equal to 4 looks like this. Vertical line, x equal 4. And then y equal x over 4. This is a line with slope 1/4. And y-intercepts going through the origin. So up 1 over 4. So I want to connect my dots here. Okay, so that's y equals x over 4. And the other one, negative x over 4. So this, instead of going up 1, it's going down 1 over 4. And so something along those lines there. Now, the volumes whose base is between these curves, so the base is this triangle right here. Okay, but then it says that the cross sections that are perpendicular to the x-axis, so they're perpendicular cross sections to the x-axis. Okay, so a cross section that's perpendicular to the x-axis, and the cross section is a square. So what do we know about a square? Well, a square, all 4 sides are equal, and all angles of a square are 90 degrees. So if I draw a little square here, try to do my best, that's kind of what that looks like there. Okay, so what does this shape actually look like? So you don't have to do this, but I'm going to draw this in a way that maybe it looks a little more real to you. So I'm going to try to do my best at drawing 3D. All right, so let me try to draw 3D here. So I've got my y-axis, and then pretend like, now we're looking at this x-axis and it's kind of coming out towards you, okay? And so let's see here. We've got the line here coming out, and we've got the line here coming out. Okay. I think that looks pretty good, yeah. So that looks like it's perpendicular, right? So that's what we're shooting for. And so then we take an arbitrary x value here. So some arbitrary x value there. And what do we say at an arbitrary x value? We had a actually a square. So I'm going to try my best to draw a square for us. Let me copy this. Get my angle perfect. So that seems like it could use a little bit more height to make it a square better. Okay, so that looks like a square there. All right, so what's happening here? So as your x values increase, so they start here and they go out bigger and bigger and bigger going this way, your squares get bigger. Like you can see down here, like your square is not very big here compared to what it was. All right, and you can even see here that your square is even that much bigger. We'll see if I can duplicate. So what you can see here, if I drew this perfectly, it would line up exactly like this. So let me see if I can't make that work. You know what, let me delete this real quick, and I'm going to connect all these dots to save us a little bit of time. Okay. Now I'm just playing around is what it looks like. so you can kind of see, like if I do different colors for the different squares, so I got a little square there, and maybe we've got this orange square here. It's a little bit thicker, a little bit bigger square, and then this red square right here. This is our biggest square, because it's based off of that biggest x value. This is the x there. You got an x here for that little one in here. And then you got an x here for that little one in there. And so you can kind of see this looks like a kind of like a slanted over pyramid type thing. So it's an actual three-dimensional shape. All right, and you just what you're doing here is you've got all these little squares inside here, and so they've got this width, this delta x width, this change in x, that delta x, and you're summing up all those squares from at x equal to 0 all the way out to x equal to 4, because that's where we stop at. Okay? So the formula says to do what? It says that the area is equal to or the volume is equal to a to b of a of x dx. So really all we got to do is figure out what a and b are, which we know right now that it's 0 and 4. Okay, so we got that. Integral from 0 to 4. We know we're integrating with respect to dx because we're perpendicular to the x-axis. So we have dx slices perpendicular to the x-axis. And the area function is the area of a square. Well, how do I get the area of a square? Well, what I need is some side and another side. So area is equal to the side squared, right? So really all it amounts to finding is this distance between this upper line here and that lower line there for some arbitrary x. Well, for some arbitrary x in our picture here, say we pick some arbitrary x in here. If I go up to this point on the line, what is that point on the line? Well, that's x comma x over 4, right? That's satisfies this equation. What about down here? This is x comma negative x over 4 down here. So how do I find the distance from here to here? Because if I know that distance, then I know the length of that side, don't I? So the area function, a of x, is equal to what? Well, the side squared. So what's the side squared? Well, it's the top minus the bottom. So the top, x over 4, minus the bottom, okay, minus negative x over 4. And so this becomes x over 4 plus x over 4 squared. So that's going to be 2x over 4 squared, which is x over 2 squared, and that reduces to x squared over 4. So my area function, a of x, is x squared over 4. So that's x squared over 4 here. So now all I have to do is integrate, and if I integrate, I get x cubed over 12 from 0 to 4. So that's 4 cubed over 12 minus 0 cubed over 12, which is 64 over 12. And that reduces to 16 over 3 units cubed. Okay? So 16 over 3 units cubed. So that is the volume of that weird shape right there that I tried to draw for you in a 3D. So kind of cool that we can find the volume of a shape using calculus. Okay? So that's an introductory idea there. Now, what if instead of squares, you had another shape? So maybe instead of squares, you had the cross-section be circles. Okay? So make the cross-section circles. So what's going to happen now? All right? So now, in my 3D version here, to think about what this is going to actually look like, if you will, indulge me for a second. So the x, pretend it's coming out at you. So I've got my cutoff again at 4, right? So I've got this coming out here. I've got that coming over here. And then that coming in there. Okay, so some arbitrary x in here between 0 and 4. Now, if it was a circle cross-section, so circle cross-section would look like this, okay? So what happens as you get closer and closer, the x gets closer and closer here, well, your circles get smaller and smaller until eventually they end up at a tip there. Your biggest circle, once again, the biggest circle is going to be at the edge. Okay. So the biggest circle is at the edge here. All right. And so whatever that is. All right. So really, geometrically, what's happening, it looks like we're getting a cone. Okay, do you see that? You see how this is kind of a cone here? So geometrically, what it's creating is this cone. All right? So how do we do this problem? So let's draw the 2D scenario going on here. Once again, we 1, 2, 3, 4. We go out to 4, and then we've got our line. Our line comes down and our line goes up. I think this was the y equal x over 4, and this was the y equals negative x over 4. Remember, we had the vertical x equal to 4 for that. And what do we want? We want an arbitrary x in here for our cross section is perpendicular. And what type of shape do we have for our perpendicular? It's a circle. Okay. So how do I find the area of a circle? When I think about finding the area of a circle, what I really need to find is the radius, right? So what is that length here? R, what is that R equal to? Remember, area function for a given circle is pi r squared. So I need to find R in terms of the arbitrary x that I have here. Well, that distance R is literally the distance from the line here to the x-axis. So that is exactly x over 4, right? So what does that tell me? That tells me that this area function in terms of x is x over 4 squared. Okay, so once again, this radius r is the distance from x over 4 to 0. Okay, so that's the exact radius for some arbitrary x value. Okay, and so what do? We sum from a to b to get the volume of a of x dx. Really, the hardest part of these problems is coming up with a formula for your area. So if you know pi r squared, you know side for area here is s squared, then what you got to do is figure out how do we figure out the length of the side in terms of x, just like how do we figure out the radius of the circle in terms of x for some arbitrary x value. Okay, and it ends up being that distance there. Okay, so you got to kind of know basic geometry formulas there, and there'll be a formula sheet that you can download. Okay, so this becomes summing all of the circles from where? From starting at 0 and summing all the way up to 4. Okay, so you're going to sum from 0 to 4 all the circles, pi, and then x over 4 squared dx. Remember, the circles are perpendicular to the x-axis, so those are dx circles. Okay, perpendicular. Okay, so simplify here. Integral from 0 to 4, pi over 16 x squared dx. I'm going to pull the constant out, pi over 16. Integral 0 to 4 x squared dx. So pi over 16. And then x cubed over 3 from 0 to 4. So what does this get me? This is pi over 16 times 4 cubed over 3 minus 0 cubed over 3. And so this is going to be 4 pi over 3 is what this simplifies to. Okay? So pretty powerful right there. All right, so that, my friends, is the area of that cone. Okay? Let's see if we can find the volume of another shape. So let's do this. Let's find the volume of the solid whose base is between y equal 10 and y equals x squared plus 1. Okay, and has cross sections that are perpendicular to the y-axis in the form of half circles. Okay, so a lot of information in this word problem here. Okay, so the first thing I'm going to do is I'm going to pick out the important things. So I want to find the volume. Okay, so finding the volume, all right, of a solid, the base is between y equal 10 and y equal x squared plus 1. So let's plot that real quick. Y equal 10 is a horizontal line at 10 here. That's y equal 10. Okay, so that's up at 10. Y equal x squared plus 1, I shift the parabola up 1 unit, and then we come up just like this. Now it's going to cross somewhere. I don't know where it crosses, but that's not going to be too hard to figure it out, because how do you know when two equations are equal? You set them equal to each other. So y equal 10 and y equal x squared, set them equal to each other. 10 equals x squared plus 1. Subtract 1 from both sides. 9 equals x squared. Oh, this is good. This is equal to plus or minus 3. So I know this intersection here and that intersection there are going to be plus and minus 3 for the x value. So it'd be 3 comma 10 here, and this would be negative 3 comma 10 there. Okay. Now, what else do I know? Cross sections. My cross sections are perpendicular to the y-axis. If I'm perpendicular to the y-axis, right, if this is the y-axis, to be perpendicular is to look like this. So my cross sections, oh my goodness, what are we dealing with now? With what type of cross sections are we dealing with? We're dealing with dy. So if I have y-axis perpendicular, that tells me I'm dealing with a dy. So I need to get everything in terms of y. Since I'm integrating with respect to y, would it make sense that I would want the function in terms of y? Right now I have y as a function of x, right? So I want to fix that. I want to fix this to be in terms of y. So that means I need to solve for x here. So to do that, I'm going to subtract 1 from both sides. And so I have y minus 1 equals x squared. And then what do? I square root both sides. When I square root both sides, I get the plus or minus square root y minus 1 equals x. Now, what is what? You might be asking yourself. And that's a great question to ask. So there's a positive side, okay, which is the plus, that's the x equals plus square root y minus 1. And then there's the negative side, which that is the x equals minus square root y minus 1. That's where that plus and minus comes into play, okay? So what kind of cross sections do we have? Now that we know our base here, remember to find that distance here, we do right minus left. Right minus left gets us that distance from previous videos. Remember, we're dealing with a dy. Okay, the cross sections are half circles. So to find the half circle, I do 1/2 of pi r squared. Okay, so what do I need to figure out? Well, do I need to figure out this entire distance across here? No. Think about a half circle, okay? So think about this half circle here. So let's just, for a second, imagine this right here, okay? Imagine we're trying to find the area of just one half circle, Okay, so we're just trying to find the area of this 1/2 circle. How do I do it? So for some arbitrary y value, right? So this is some arbitrary y value. How do I find that distance? Well, remember, it's just the radius squared. So it's this short little distance right here. So what is that distance? Well, it's from 0 to what? X equals what? Square root y minus 1. Okay? And then you square it. All right? So a of y is 1/2 pi r squared. So what is your r here? That little radius is the square root of y minus 1, and then you square that. Now, you might be asking yourself, well, Mr. Clark, what if I had picked the other side over here? Well, that would be okay. The only difference is this would be negative square root y minus 1. But what happens whenever you square a negative? When you square a negative, what do you still end up with? You end up with a positive. So they're both still positive. So the square and the square root, these kind of undo each other here. And so I get 1/2 pi times y minus 1 for my arbitrary area formula here. Okay, and like I said, that's the hardest part of the problem, is getting that arbitrary area formula set up. So now what do? I integrate. So I'm summing all the arbitrary rectangles from where? From 1 up to 10. So all the rectangles from 1 up to 10. So from 1 to 10 of the area formula, a of y dy. So that's the integral from what? Remember, it was like bottom to top, right? And then it was like right minus left kind of thing, but that's where we figured out we used the particular cross section. The half circle told us what the formula would be. And so that ended up being from 1 to 10 of, and then what was a of y equal to? It was 1/2 pi y minus 1 dy. And so this will simplify. Pull the 1/2 pi out. 1 to 10 y minus 1 dy. So that's pi over 2. Integral of y is y squared over 2. Integral of negative 1 is negative y from 1 to 10. And what's that going to be? Pi over 2, and then 100 over 2 minus 10, and then minus 1/2 minus 1. And if you simplify all that, you get 81 pi over 4. Okay, so you can do the math there. Now, say instead you make the cross section quarter circles. Okay, make the cross section quarter circles. So now the picture, okay, we still got the picture going on here. So y equal to 10, and then we started here at 1, right? And now the cross section is a quarter circle. Once again, we're still cutting dy's here, but you think about finding the area of a quarter circle. How do you find the area of a quarter circle? Well, you take the whole area, pi r squared, and then you divide it into fourths, right? So and that gets you the area of 1/4 circle. But what's different about this problem, okay? Our r is that entire distance across. It's not just the halfway across like we did with the previous one where we just needed to find one side of it, right? So the radius now has changed. It's all the way across, just like it's all the way across here. okay? So how do I find that distance? Well, remember, we said this was x equals square root y minus 1, and this side was x equals negative square root y minus 1. So aren't they going to cancel? Well, let's see here. How do we do it? It's right minus left. So right minus left gets me square root y minus 1 minus negative square root y minus 1. And so that ends up giving me 2 square root y minus 1 for that radius. Okay? And so now I know I can plug this into my formula. So I have pi r squared, so that's 2 square root y minus 1 squared over 4. So that's pi, and then I have 2 squared, and I have square root y minus 1 squared over 4. Well, 2 squared is 4, and 4, those cancel each other, right? And so I'm left with pi times y minus 1. Okay? And so then at that point, I've got my a of y function, and it's the same old, same old. I integrate from 1, starting at the rectangle 1, and then I add up all the cross sections that are perpendicular. Okay, remember, we think about a definite integral is summing. We're starting at 1, and we're adding all of these shapes here. What are those shapes? They are 1/4 of a circle area, right? So 1/4 of the circle area is represented by pi times y minus 1, okay? And then I sum up all of those objects from 1 all the way up to 10. Okay, so I'm summing up all those from 1 all the way up to 10. But then I've got to add that thickness in there to make it volume, and that's where that dy comes into play. And if you integrate this out, you get 81 over 2 pi. Okay? So you can run through the math to check yourself, make sure you understand how to do that. It's the same exact operations, basically, is what was going on here to integrate to get to this final answer there. Okay, so try to do that one yourself.